All right, so welcome to part one of our series where we're going to be doing a revision of the topics in CSEC Chemistry. In this revision series, we're going to be taking some questions, and what we'll be doing is to provide you with the explanation of the answers and also give some insights on some other pointers as to ensuring that you're successful in your CSEC exams. So I am Mr. Thomas. I'm founder of Buckle Down Tutoring Services, and we do our one-on-one classes or sessions, online, face-to-face. We also have our small classes that you can be a part of, online and face-to-face. And so today we're going to be looking at states of matter. We are going to dive right into it. It says, Christina wanted to provide evidence that matter is made up of particles. And so she set up a glass tube as shown below. We don't know who Christina is. She just want to prove the evidence. Yeah? You go, Christina. Let's cheer for Christina now. A white ring was formed in the position indicated. So when we look at the position right here, this is what they're talking about, that white ring. We want to zero in a little bit about this experiment, this evidence that she's going to be using to say that, matter is made up of particles. That is just one of the pointers coming out. We have three others. They say that matter, the particles that make it up, they're in constant motion. A matter of fact, temperature affects the motion of these particles. 3, they also mention that particles in the matter, they're attracted to each other. So there are some forces of attraction. In the various different states, the attraction may vary, right? And we're going to be looking at that later. And then finally, particles in matter, they do have spaces between them. And again, the state at which the matter is, it will affect the amount of space that you have between the particles. So this setup, you have a glass tube. We have 2 cotton wools soaked in 2 different substances. One was soaked in ammonia, concentrated ammonia. One in which you have concentrated hydrochloric acid. Pause the video. Are you able to write down the formula of these 2 compounds? Yes. If you did have NH3 for ammonia, give yourself a clap. That is indeed the formula for ammonia. If you had HCl for hydrochloric acid, then of course, definitely you would be correct. So these 2 substances, they would have been dipped in the concentrated solution and simultaneously, in math we do simultaneous equations. We're solving 2 equations at the same time. So we're putting these cotton wools at either end of the glass tube at the same time. And then of course we're going to be placing that rubber band and we seal the ends of the glass tube. Now, while she did this experiment, we'll talk a little bit about what is happening. So for some reason, we have this white ring forming, right? And so when she placed liquid inside, the contents of those will become a gas. So we have the gas and we have wind inside or air inside of this glass tube. And so where you have either of these solution being soaked, you would have considered that high concentration where you have a lot of the particles. So to one end, I have a lot of ammonia particles. To the other end, I have a lot of hydrochloric acid particles. So we know particles, they are basically moving. right? They're in constant motion. And so with that being said, they're going to be traveling in the opposite direction, because at opposite end you would have low concentration of both. Now while they're traveling, more than likely you have, or you would have had, a reaction happening between the particles. A matter of fact, that's the only way you will get that white ring. That white ring is formed due to the reaction between ammonia particles and hydrochloric acid particles. So see it, Christina did have something, yeah man, she was on the right track, because this proved the only way the white ring could have formed is if particles are actually in motion in this case. Because if this white ring is happening due to the collision of the particles of the hydrochloric acid and the ammonia, and they were placed at opposite end, it must mean that they're actually moving. So it says, name the compound that makes up the white ring. And the compound that makes up the white ring, we call it ammonium chloride. The next part says, or part 2, it says name the process occurring in the apparatus and give its definition. So the name of the process would have been diffusion. And we know that diffusion can happen both in liquids and gases. The definition. So it's the movement of particles, and this is usually something that students are able to recite. So it's a movement of particles from a high concentration. And when we say high concentration, we are talking about where we have a lot of the particles. So if you notice, on either end of this glass tube, we had a lot of the ammonia particles. We had a lot of hydrochloric acid particles. So we move from a high to a low concentration where we have small amount of these particles or no particles at all, until they are evenly distributed. Now, I think we actually came out with the answer to part 3 already. It says, by referring to particles, explain why the white ring formed. Now, the white ring formed because the particles from the ammonia started to travel to the opposite end, likewise that of the hydrochloric acid, and where they had that collision, or where they meet, or where they collide or react, that's when you have the white ring being formed. Right? Now we can talk a little bit about it in terms of, sometimes teachers provide this as a lab, and you have to accurately draw where the white ring would have formed. And if you notice, the white ring is formed closer to the hydrochloric acid than to that of the ammonia. Now, this is due to the molecular mass, or the molar mass of these substances. Now, if you take, for example, ammonia, and what was the formula for ammonia? We did say NH3. So nitrogen, the atomic mass is 14. Each atom of hydrogen, which we have 3 of them in the molecule, will be providing or adding to the mass, and so each is providing 1. So when you think about the mass of ammonia, you're looking at about 17 grams, and usually we say per grams per mole, the molar mass. In terms of hydrochloric acid, we're talking about hydrogen again, and this time chlorine. Chlorine 35.5 for the atomic mass. 1 hydrogen is 1. When you look at that, that is 36.5. So in terms of the mass of these 2 gases traveling, ammonia is basically half the mass of hydrochloric acid, which will cause it to travel much faster. And so it will cover for a far distance than the hydrochloric acid, and so the white ring will form closer to the hydrochloric acid. Paul. You don't know where Paul are going with it now. But you know what Paul did? Paul measured the length of 2 strips of papaya. Now in Jamaica we say papaya. Yeah, that fruit, you know, it has a lot of benefits. A lot of persons may not like it, but it has some nutritional benefits. Some persons even utilize the leaves. And after him cut up them strips of papaya, 2 strips him cut up, he placed them in a beaker of water as shown in the diagram below. So Paul, Paul a scientist, you know. Watch what them asked Paul now. He said in the second beaker, you're asked to draw how the papaya strips would have appeared after Paul had left them in the water for 30 minutes. So Paul gone about in business for 30 minutes. What do you expect these papaya strips to look like after 30 minutes? Put your comment in the comment section. What you expect them to look like? Pause the video. So if you said that these strips should increase in size, so in the beaker to your right, if you're drawing the papaya strips, you should draw them larger. So they should look larger than those that are currently in beaker to your left. And let's talk about it, because we're supposed to explain the reason for the change Paul observed in the strips of papaya. Now we have another phenomenon, another evidence that can support the particulate theory of matter, known as osmosis. Oftentimes I ask students, is osmosis different from diffusion? Is diffusion the same as osmosis? What do you think? If you mention that yes, osmosis is a form of diffusion, then you're correct. Osmosis is a form of diffusion, but it focuses on water molecules, right? So once you're talking about water molecules, you're going to be talking about osmosis. And what you find is that the water molecules are moving from a high to a low concentration. Now, if you're to understand where the water is moving, you need to decide which scenario or which set of substance have a high concentration or a low concentration of water. So let's really examine what is happening inside the potato strips. Now, and I made mention of potato strips because usually we use potato as well. So it's papaya strips, the papaya strips. So when you look at the papaya strips, and you have to work with me now, you're thinking about it, but it's a plant. In the plant, you have cells. So inside of these strips, you're going to be having cells. What is inside of the cell? One of the organelle that holds the other organelles is the cytoplasm. And the cytoplasm is comprised of a lot of water. About 70 or 80% of the cytoplasm is water, right? But Paul placed the papaya strips in distilled water. So the water in the beaker has more water molecules than the cells in the papaya. Now there's something critical about osmosis. It occurs across a differentially permeable membrane. And we're talking about our cell membrane. Remember, the cell membrane, if you can link it, can you tell me? Yes, exactly that. What it does is to regulate the movement of substance in and out the cell. Not everything that we're going to want coming out in the cell. Not true. And so with that, water is one of those substances that basically, water to be able to move in and out freely. Prevent water. Water is benefits of water, it's up there. We can go on and list 1,000 benefits. Yeah? So inside the cells of the papaya, the water is compared. And that's why I said if you can identify which one has the higher molecule of water concentration, then you're good. It has less water molecules than that of the water in the beaker. And so water from the beaker is going to go into the cells of the papa, right, through the process of osmosis, causing it to increase in size. And that is why after 30 minutes, I don't know where Paul gone. Paul just throw in the papa and just walk down about in business. Yeah, but we are going to be seeing an increase in the size. Yeah, so we're supposed to name the process, and we did indicate that it is osmosis, a form of diffusion. So watch me now. Part C says you decide to preserve some fish using sodium chloride. Can you tell me the formula for sodium chloride? Can you tell me if sodium chloride, what type of compound is it? Is it an ionic or is it a covalent? Those things you should be able to do, right? So going forward, yes, NaCl. If you got that correct, then you are on the right track. Also, it's the common name for it's a scientific name for the common table salt. It is a ionic compound. Ionic because you have sodium in this stage. I normally tell students you can use the concept of a metal and a non-metal, but really a ionic compound is between a cation and an anion. And later on, when we look at bonding and all of that, we do that revision, you'll get more insight on that. So for now, we're saying metal and a non-metal. We see sodium, we see chloride, which is chlorine when it is bonded. Another important point. So on the periodic table, you'll see chlorine. When it is bonded, we use that IDE name known as chloride. Cool? Oxygen, when it is bonded, oxide. Nitrogen, nitride. You get the concept. So sodium chloride is an ionic compound, and we use it in the whole fact of preservation. When we think about preserving, you know, we want to preserve our culture. We want to preserve the environment. What are we doing? We want it to last longer. Not true? So if we want the fish to last long, because sometimes when we purchase this item, we don't prepare it the same time. Now, in Jamaica, ackee and saltfish, you know, is like our national dish, right? We enjoy that. If you come to Jamaica and you have that dish, you won't be disappointed. Now, what is it about the salt? How does the salt, this sodium chloride, works as a preservative? It goes back to the concept of osmosis. When you place the salt on the outside of the fish, right? And we can give a little joke. Them always say, you never see the head of the saltfish. You know, never see the head of the saltfish and say ugly. Yeah. If you see the head, just know you're gonna run. You probably stop eating saltfish. But when you place that salt outside of this fish, the cells, you're going to have a concentration gradient being created because you now have less water on the outside than on the inside. So now you have the cytoplasm having more water. Just like the papa, the fish, it has a cell membrane. So what do you think the water does? The water is going to move from the inside of the cells of the fish onto the outside, causing the fish to be drier. How does this, you might be asking, how does this deal with preservation? You jump across to your biology again to get your answer. You know, and they say this in biology, that a disease we have what we call a disease triangle. 3 things for a disease occur. You need the host, you need the pathogen, and you need the favorable environment. Now here's the thing. Food spoilage is caused by some bacteria, and them are the pathogen where we are talking about, and they love moisture. So they like moisture, and with moisture they get to multiply, they get to reproduce. You know, so every organism, we can't cuss the bacteria them, you know. They basically try, you know, survive just like how we as humans try to survive. They want to reproduce. They want to continue their population. It's a natural thing. So, but we want our fish. We don't want, when we put on a fish, 2 seconds, it's not edible. It's like when money gone down the drain. Shellfish expensive now, not true? How much a quarter pound? Tell me in the comments. So, when you place that salt on the outside of the fish, you basically allow for that concentration gradient and the water will come out, and that will help because microorganisms that cause spoilage requires the concept of a moist environment to strive. So with that dry, of course they're not going to be able to reproduce. They will, but you're basically slowing down their growth. Not true? Yeah. So to relate to that as well is the same thing you do when you throw the salt. In a Jamaica we say bullfrog. Yeah man, so a bullfrog coming in your house is not saying that you know Obi and you're gone for the salt. But what you do is to sprinkle the salt on the back of the frog. And this frog will try to escape himself, run from you. And he's running to try and get the salt off because his body is going to cause him to dry out. We use the term desiccation, and you don't want that. So that's all of that is actually a chemistry I do the same. And I'll be the person I work, a chemistry. Right? So then sprinkle the salt. Yeah. Only time you're supposed to sprinkle salt. Yeah. And when you do that, the organism, tries to get out. Part A says complete the table on information about these 3 states of matter. We know solid, liquid, and gas. And they have some properties. Volume. And we say, what is volume? Can you tell me? If you said volume is the amount of space occupied by an object, you're indeed correct. Right? And so solid, if I have a piece of, if I have my eraser, and I have it in one room and I move it to another room, whichever room I have it in, it's going to take up the same amount of space. And so it has a definite volume. Liquid, sometimes students have a misconception and say that the volume changes. But if you have a bottle of Pepsi 5 milliliters, and you take that 5 milliliters in the bottle and pour it in the cup, do I get 10 milliliters? Do I get 6 milliliters? No. The volume will stay constant. So it's also definite. So not because it's a liquid, the volume will be the same. Now with the gas varies based on the fact that gases tend to fill their container. And so if you move it from a smaller to a larger container, the volume will increase because it's going to fill the container. Right? In terms of arrangement of particles, the particles in a gas they are arranged far apart. Yeah? They tend to space out from each other because they don't like gases, they don't like other particles. So they have less attraction to particles, so they tend to move at random, right? And move as far away from another particle as possible. Yeah. The particles, them are social distance. Yeah, man. None of them here about COVID. Solid. The particles in a solid, usually students know this information, we're revising, they're closely packed. Very, very closely packed, tightly packed if you want to use that word as well. When we think about the energy of particles, because the particles in a solid, they do not possess a lot of kinetic energy. And so they're moving, a matter of fact, when you think about how the particles move, they say solid, they vibrate in a fixed position because they don't have a lot of energy. There's a little relationship between the energy that they have and the attraction. So the more attracted they are, the less energy they have, right? So liquids, if you want to give a definition or explain, sometimes I tell students to just do a comparison. So they would have more energy than the solid particles, but less than those of a gas. So by referring to the particulate theory of matter, and we did say them. 1. Matter is made up of particles. 2. The particles are in constant motion. Temperature affects how fast these particles are moving. 3. The particles have some forces of attraction between them. And of course, 4. There are spaces between the particles. Them say each of the following statements. So you're supposed to use the theory to explain each of the statements. Now, oxygen gas. And let me pause right here to take into consideration, this is another type of compound. It's actually a covalent compound. It's actually one that we call a diatomic element. What do we mean by that? Whenever oxygen or the other, we have 7 of them, 7 diatomic elements. Whenever they are in the environment, they tend to bond to another atom. They have to find one next atom. They don't stay by themselves. You understand? And so when you write the formula, oxygen gas, it is O2. You have a subscript of 2 following the symbol. And that's very important. Right? Can you name the other 6 diatomic elements? Tell me them. Now, if you mention nitrogen, that's correct. If you mention hydrogen, you're correct. If you mention chlorine, fluorine, bromine, and iodine, you're indeed correct. Those are the other 6 diatomic elements. So they always have that subscript of 2, because once you have one of those atoms, they will basically bond to another atom. So going back to the question, it says, oxygen gas is very easy to compress. So when we think about compression, we're thinking about bringing things closer. Yeah? Bringing it closer. So when you apply the pressure, you can do this easy with oxygen gas, because we know that particles, especially gas particles, have a large space between them. So oxygen gas would have a large space, and so it should be easy to compress. As a matter of fact, that's how they compress the gas and put it in your cylinder. Your Gas Pro and your IGL. You know the Gas Pro in Jamaica? You know the Gas Pro song? Sing it for me. 1888. Yeah, that's the number you need to know. But that's not the number you need to know. You need to know Buckle Down Tutoring Service number, because what? You have to get prepared for your exam. At this point, if you're enjoying the video, you're working with us, like, subscribe, and of course share. A solid lump of iron has a high density. John Star talking about a lump of iron. Now, one thing that we can relate to is that all metals are usually solids at room temperature, except one. Can you tell me which one is not a solid at room temperature? Yes. If you guess that one, mercury, you're indeed correct. And mercury, we use it in our thermometers because of the property that it has. It expands. Yeah? So, why a solid lump of iron has a high density? Let's use that word gone over geography. No, we're talking about population density. So if we talk about population density, we are talking about how much people in our geographical area. So watch me now. When you think about the closeness, high density, or the area is so dense. So China, the US, some of these countries, Japan, they're so dense in some areas that they might tell people say you need to move out or stop have children, right? Because you don't want to get overpopulated. The resources can't manage. So going back, linking it. So the solids, the particles we know are very close together in our solid. So they are very dense, right? So that is it. Nitrogen gas. And I hope you made that connection. The moment you saw nitrogen, you should have said, oh my, this is one of the diatomic elements that Sir just mentioned. So can you tell me the formula for it? Definitely. It is N2. It readily takes the shape of the container that it is in. And we know gases, they expand to fill their container. They have less forces of attraction, and the particles are moving, constantly moving. Yeah? Beautiful. Part C, it says, you know, the diagram below shows the 3 states of matter. Can be changed from one form, or how the 3 states of matter can be changed from one form to another. The letters A, B, C, and D represents the process that brings about the changes. So we see A, B, C, and D. Now from a solid to a liquid, what are we doing in terms of energy, in terms of temperature? If you said it, yes, we are increasing the temperature. We are adding heat. Yes? And by doing so, we are causing the substance to move from a solid to a liquid. Now, if you think about it, the particles in the solid, because they get that heat energy, they get less and less attracted to each other, so they break further and further apart. And so at that point, it changes to a liquid. When this happens, we call it melting. B, a liquid move into a gas. Yeah, man, we do this all the time. We're boiling some water to put on some tea. What kind of tea you drink? Cersei? Lime leaf? Orange leaf? Guava leaf tea? Coffee? What is it that you drink? Tell us. Mint? So the water on the stove, you'll see it evaporating. And it is not the hydrogen. If you know anything about the molecule of water, it is H2O. It's not the hydrogen separating from the oxygen. It is one molecule getting enough energy to break away from the rest of the water molecules leaving, and it leaves as a gas. It changes its state, and that is evaporation. And let me pause to talk a little bit about boiling and evaporation. So, are they the same thing? Is boiling evaporation? Is evaporation boiling? No, they're not. There are 2 distinct differences that you need to know about boiling versus evaporation. The first one, when I boil, all of the substance is affected. When you are evaporating, only the surface of the substance is affected. Boiling has to happen at a particular temperature, and so in chemistry here we mention boiling point. So boiling point is that point where you have that constant temperature while a liquid becomes a gas. A matter of fact, if you talk about pure water, we know that pure water boils at 100 degrees Celsius. Now evaporation can happen at different temperatures. It doesn't have to be specific. And so those are the difference. So you have a water on the soil, you have water in the sea, it will evaporate. The sea doesn't have to be boiling for the water to evaporate. Alright? Gas, liquid, what are we doing? We're removing heat, we're reducing temperature, and so it changes to from a gas to a liquid, and that is known as condensation. From a liquid to a solid, we call that freezing. I'm sure you would have gotten all 4 correct. Number 2. And then of course on our diagram, we have the concept of sublimation. Now if you look at it, it is when a substance moves directly from a solid to a gas. Now you're asked to name one substance that sublimes. I tell you in a Jamaica, man. If you don't know the Jamaicans them in here, if you don't know, we know we're going to say camphor ball. We know that thing? Camphor ball, popularly known to us in Jamaica by that name. Scientific name is naphthalene. And, you know, sometimes we put that in the drawer, you know, for ward off the roach and the rat. Sometimes these organisms, these pests, cut up the paper, cut up your if you're not careful, and cut up your passport, and cut up your birth certificate, things like that. Important documents. So we may place these little balls inside, and the thing about them, they give off the vapor, which give off a scent that will repel. It's like a repellent. And so it moves from a solid to the gaseous state. So that's one example. Another example is the one that we spoke about earlier, ammonium chloride. That's also an example. That white ring, if you heat that white ring that was formed, it will basically turn back to a gas. So it moves from a solid, so that solid state, where you have that white ring, it can move right back to a gas. Others include the dry ice. Yeah man, carbon dioxide. When I was younger, they used to put those on the top of ice cream. Yeah, so you get the ice cream, and we take off the dry ice, and we go around at the corner, and we put it in a little water, and make a little smoke, and we say we do a little movie where, you know, like a horror movie, and you see the smoke come out. Or sometimes them rude and we wrap it up in a paper and say we are smoke. And so because this solid becomes a vapor, you see the white vapor coming off and it look like you have smoke. Not true. If you did do that, let me know. Or if teenagers are doing that still, you can let me know. Another, it's sublimation is very important to us because that is how we utilize our solid air fresheners. And some of these air fresheners, what the company realized is that they can equip it with a little, maybe a fan installed on their air freshener device. Because when you have the solid will become a gas, and then the gas is basically blown, and that's how the room smells sweet and nice, and you know, it gets rid of the scent. Part D speaks to a heating curve. Now, this is a heating curve of a substance X, and it's given below. They say use the curve to answer the following question. The moment CXC or any question your teacher provides you with a heating curve, think about something moving from being heated from a solid to a gas. Right? Now, on any heating or cooling curve, which the cooling curve is the opposite, you're moving from a gas to a solid. These slant lines represent the state of matter of the substance. In this case, these are the state of substance X. So right here is solid, right here is liquid, right here is gas. Now, just like the curve, sometimes you take out a bottle of water out of the refrigerator or a ice. It has been frozen and it starts to melt. When you're heating that, the temperature will not increase until the last drop of ice becomes liquid, and then you see the temperature starts to increase. So at that constant temperature, that's what we call the melting point. So that constant temperature as a solid becomes a liquid is known as the melting point. Right here, when you have, this is a closed system, where you have liquid and gas until that last drop of liquid becomes a gas, then the temperature will increase. This point where you have that constant temperature, right, is called the boiling point. So now we have a little bit of information. When you're plotting, you can be asked to plot a heating or a cooling curve. Usually time-related variables are placed on the x-axis, and of course the temperature will be on the y. So that's why we have it looking like this. So if you notice, this represents minutes. So 2 minutes, 4 minutes, 6 minutes. It says in what state does X exist at 40 degrees Celsius? So we find 40 degrees and we bring it right across until it touches our curve. And it touches our curve, if you can recall what I said. Say it. That. So solid, liquid. So we know that substance X at 40 degrees, it's going to be a liquid. Let's see your best, or if you understand in its entirety. What would be the substance, what would be the state of the substance at 60 degrees Celsius? Give you some time? Yes. If you said a gas, then you're indeed correct. At 60, straight across right here, it would be a gas. So it asks is the other question, part 2, asks, what is the boiling point of X? And as I said, that's the constant temperature. And if you notice, the line constant. So while time is in over a period of time, so at 14 minutes, 16 minutes, 18 minutes, we're still at that constant temperature for substance X. We don't know what substance X. So the boiling point would have been right here. Let's go back and examine this. We're seeing 1 centimeter representing 10 degrees Celsius because we move from 50 to 60. So how much are these lines in the middle? So this must be 2 degrees Celsius. So 52, 54, 56, 58. And so the boiling point would have been 58 degrees Celsius. What you can do, figure out the temperature also for the melting point. Can you figure out the melting point? Let me know in the comments what is the melting point of substance X. Using a circle to represent a particle of substance X, in the space below, draw 9 of these particles to show how they would arrange in X at 5 degrees Celsius. And students will be saying, but how do I know the particles? How would I know they arrange in substance X at 5 degrees? Of course, you go back, visit here, because remember, initially the question says using this heating curve to answer your questions. So each question that you're going to be answering, you would relate to the curve. So I find 5. 5 is about right here. And of course, I now recognize, and if you said it before I did, substance X is a solid. Now, a lot of times students don't like to follow instructions. I'm not going to be doing it here because this is a PDF, but it says 9 particles. 9, not 10, not 11, not 15, not 2, not 5, 9. Use circles, not square, not star, not triangle, circles. So sometimes we need to follow the instructions of the questions because that's what you're asked to do. So you draw 9 circles, and the key is to remember how the particles are arranged in a solid. And if you just mention that they are tightly packed, then you're correct. So you draw them closely packed, and that would have been your answer for that part of the question. Now, I hope states of matter, we would have brought some little light. If you're a grade 10, grade 9, even a grade 11 student, or if you're somebody just doing chemistry for the first time, I hope this video would have actually shed some light on states of matter. We're going to be doing this series, call it the revision of the different topics. Next topic would have been mixtures and pure substances. So you can look out for that. I want you to subscribe. I want you to like the video, and I also want you to share, and you can comment. Remember, Buckle Down Tutoring Service. I'm Mr. Thomas. That is it.